Welcome, my name is Matthew, and in this series of videos I'm going to talk to you about graphs of polar equations. And I'm recording this as a little mini 5-part series so that each of the videos can be smaller. I don't know why it is that at this point in this particular pre-calculus series I've decided to start chunking my videos into these shorter recordings. Maybe it's because it's already 8 o'clock at night and I'm already tired of recording videos. I'm getting old, I guess. I don't know. But anyway, for this particular section, which is called 6.4, graphs of polar equations, I'm going to make 5 mini videos. So that the first one in particular is going to be very short. But each of the subsections that are contained in this little mini series, they contain a lot of detail, and so instead of having you click into the timestamps in order to access the different parts of this video and to make them more easily searchable, I thought, let me just try chopping this up into 5 smaller pieces. Plus, that way, if I get sick of recording a couple of sections in, I can stop and very easily pick up with 3, 4, and 5 later. So in this series, I'm going to talk about circles. So these are going to be polar equations. So we'll talk about circles, which are of the form r equals a sine theta or a cosine theta. Then the next section will be about the 3 tests for symmetry on the polar coordinate plane. And I'll work out an example where I start with an equation, I perform the 3 tests, I'm going to plot some points, and then depending on which of the symmetry tests get passed, I'll then utilize the symmetry in order to potentially draw some more of the graph. In the third section, we'll... now this list that I made says that I'm going to use symmetry tests to graph limicons. So we'll just see where the breaks actually occur. I'm pretty sure that we're going to talk about the 3 symmetry tests, and I'm going to show you an example. That'll be in section 2. Section 3, I'm actually going to graph some limicons. In section 4, the 4th segment of the video, we're going to graph Rose curves. In the 5th section, we'll graph lemniscates. And then, actually, there's going to be a 6th section where I'm going to graph a sideways facing parabola for you. Is it still a parabola? Is it half of a hyperbola? I'm going to call it a parabola. It's going to be a parabola on the polar coordinate plane. See why I'm going to chop this up into smaller videos? Let's start. We'll just take them one at a time. So be patient with yourself. It's a lot of information. Take some really good quality, organized, detailed notes. Write in some additional commentary into your notes. Annotate your notes. I'm not going to write down everything. Some things I'm just going to say, and I'm not going to write down. You're in charge of knowing what to write down. The other thing that I'm going to do in this series is I'm going to be using Desmos.com, Desmos.com, for all of my graphing. I don't have an emulator for either of my TI calculators, and instead of holding it up in front of the camera and trying to focus in on it, I'm going to do a split screen and show you some of these graphs on Desmos. Also, I started out trying to hand draw these graphs. Not good. It's not pretty. On paper, I can graph them fairly well, but something about drawing them on the iPad, it wasn't working for me. So, if you want to be sort of playing along and typing these things into Desmos, or if you want to save any of the graphs in there, you'll need to have created an account. I'm pretty sure it's still free, but I was able to log in, type in all these graphs, and then because I had already logged into my account, up at the top of the screen you can see it says Polar Trig Graphs, and then Save is kind of ghosted. It's because I've already saved this. So I've got all of these graphs typed in already. If you want to, I don't like when that happens. See, it's like relocating that equation. I don't know if that's even where that's supposed to go now. Great. It's supposed to go 1 up from there. Right there. Okay, stay. If you want to type these in advance, you're welcome to. I'm obviously going to be showing you my screen, so you'll get to see what all of them look like. I'm going to freak out, though, if this thing... I don't know why it keeps relocating my graphs. Okay, anyway, now that they're totally out of order, let's go back into the notes and start out by taking some notes. There we are. So here's our first equation that we're going to graph. R equals, excuse me, 2 sine theta. And there's a table down here that I have already filled in with some R values. I would like to take these coordinates and plot some points. Try to make these videos a little shorter by having already done some of the work in these 5 or 6 segments that we're about to look at. So let's plot 0, 0, which is right at the pole, in the direction of pi over 6 going out 1 unit, in the direction of pi over 3 going out rad 3, which is approximately 1.7. So a little bit short of 2. Let's go there. And in the direction of pi over 2, I'm going out 2 units, 2 pi over 3 rad 3, 5 pi over 6, 1. In the direction of pi, I'm not going anywhere, so that really causes me to plot another point at the origin, or at the pole. I already have one there, so I'm not going to do that again. And then, aiming in the direction of 7 pi over 6, again, aiming in the direction of 7 pi over 6, we've got an R value of -1, so I would walk away from 7 pi over 6 1 unit, which would put me at this point again. So I'm not going to graph that again either. It appears that as we continue scrolling through theta values, even once the result is negative R values, we end up plotting the same points over and over again. So we're going to stop there at 7 pi over 6, really stopping at pi, really stopping at 5 pi over 6. Well, no, that's not true. We're really going all the way to pi, because in order, we started out plotting this point at the pole, and from there we went counterclockwise. And if we connect all of our dots with the best curve we can, if I had stopped at 5 pi over 6, this would be my graph, and I would not have closed my circle. So we do need to go all the way to pi, even though it causes us to plot the point at the pole again. That way the circle closes, and this is indeed a circle. You'll notice that the coefficient in front of the sine function was at 2, and that the diameter of this circle is 2. Not a coincidence. You can see my fabulous artistry here. What I did is I used a graphing calculator. These I did not type into Desmos, but I drew you some little sketches of these resulting graphs. So R equals -2 times the sine of theta gives us a circle still with a diameter of 2, but instead of R equals +2 sine theta, where the circle sat above the pole, here with the negative coefficient it sits below the pole. It almost seems like putting a negative in front of a polar equation like this causes a reflection over the horizontal axis. Interesting. I wonder if that remains true all the time. Anyway, R equals 5 cosine theta gives us a circle, still the diameter of 5, matches with the coefficient of 5, and cosine puts us to the right of the pole, and I am quite sure that I drew the last graph incorrectly, so I need to fix this one. At negative cosine, our circle should be to the left of the pole, with a diameter of 3. It's not quite circular. You can see why I switched over and started just graphing them online instead of hand drawing all these for you. Still a diameter of 3, but in the negative horizontal direction. X and cosine kind of go together. If you watched the previous video in the previous section, R equals x equals r cosine theta and y equals r sine theta. So x and cosine, I tend to associate those with each other, which is helpful here because the circles for cosine are to the left and right in the x direction of the pole. So what determines the diameter of the circle? That would be the absolute value of the coefficient. But who wants to write all of that out? Let's write it like this. If r equals a sine theta, or r equals a cosine theta, then diameter equals the absolute value of A. I like that a lot better. I feel like that makes a little bit more sense to me. What determines the orientation of the circle with respect to the pole? Sine versus cosine. Sine versus cosine. And if our A value, the coefficient on our trig function, is greater than 0, or I guess we don't need the word if. Let's have this format kind of match up. And A is greater than 0 versus A being less than 0. So those are the two things that are determining the orientation. And then it says, fill in the missing sketches in the circles section of the summary page. So I'm going to jump down to the very last page of these printable notes. And this is nice. These particular printable notes have a summary page at the very end. And we can draw in these sort of generic versions of these circle graphs. So here we've got A equals cosine theta. I see the cosine, so I know it's going to be to the left or right of the pole. My A value is positive, so I'll be on the positive horizontal side of the pole. Let's draw ourselves a circle as best you can. And we know that the diameter is equal to A. If you would like to depict it, or depict that fact the same way it has been shown on the right-hand side of your screen, where we sort of highlight the fact that the diameter, if my pen will work, is equal to A. You can do that in all of your diagrams or just leave that one printed version in there. For cosine, where A is negative, our circle is going to appear to the left of the pole. For the sine function, when it's positive, we're above, and for sine, when the coefficient is negative, the circle resides below the pole. Great. So there is the summary regarding circles, and you can see below that limicons are next. Let's just get back up here to the top of our notes and make sure we haven't left anything out. We have not left anything out. We filled in the missing sketches, and our next topic is symmetry. So if you would please, click on the link that is directly below me, right down there, and that will take you to the next video in this little sequence that I have regarding graphs of polar equations, and we'll talk about symmetry. See you there.